Hi, welcome back to Missing Chemistry. This is electron configuration of Vantium. Vantium is the 23rd element of the periodic table, so we're going to have to put a 23 right here for the atomic number. And its atomic mass number, the AMU, is of course going to be 51. All right. So now, since Vantium has 23 protons, it must have 23 electrons to be electrically neutral. What about the neutrons? Well, it's AMU minus protons equals the number of neutrons. Pretty cool, huh? It's easy. 51 minus 23 equals 28 neutrons. Now, before we do the electron configuration, we have to look at the subshells. The S subshell can hold 2 electrons, the P subshells can hold 6 electrons, the D subshells can hold 10 electrons, and the F subshells can hold 14 electrons. We're going to be using the off-ball principle, which is also called the diagonal rule right here. And we're going to start with the 1s, and we're going to go down the slide until we run out of electrons. So let's go ahead. 1s2, pretty cool, huh? 2s2. Okay, so we got 2 there. 2p6 and 3s2. So we still got plenty of electrons left. 3p6 and 4s2 next. All right, and then we're going to get 3d3. Pretty darn cool, I have to say for myself. Now, let's look at Hund's rule. Hund's rule talks about suborbits in the up arrows and the down arrows when you do orbital notation. So you have to put an up arrow in every suborbit of that orbit until you run out of suborbits, so you can put the down arrows. Well, 1s only has one suborbit, so we go up and down. The same thing with 2s, up and down. 2px, 2py, 2pz, you go 1, 2, 3. Now we start the down arrows, and that does Hund's rule. 4, 5, and 6. Pretty amazing, huh? 3s, up and down. 3px, 3py, 3pz, 1, 2, and 3. Then 4, 5, and 6. This is so much fun. 4s, up and then down. Now, we have 3dx squared minus y squared, 3dxy, 3dyz, 3dxz, and 3dz squared. Do we really need all of those suborbits? The answer is yes, you do. All right, because think about this, electrons, when they get excited, they can jump suborbits or even orbits. So let's go ahead and draw them in. 1, 2, 3. Pretty cool. So let's look at the noble gas notation, NGN. Argon is the nearest gas to Vantium. So let's go ahead and put argon in there. There we go. And we're going to get our valence shell right here. There's our valence shell because it includes the 4s2 and the 3d10. But when we write it, we're going to write it numerically in order. 3d3, 4s2. All right, now the quantum numbers. This is going to be really interesting. Remember that the D block is n-1. And although Vantium looks like it's in the 4th energy level, it's not really in the 4th energy level. You take the n number 4 minus 1 and you would get 3. So the energy level for the principal quantum number is actually going to be 3. Okay, the angular momentum number, the L value, is going to be 2 because it's in, scantium's in the D block, right? It's right there. So let's go ahead and put a 2 there. Our magnetic number. Now, you go minus 2, minus 1, 0, 1, 2, and then you repeat them. So, scantium was minus 2, titanium is minus 1, and Vantium is going to be 0. Yes, 0. So we're going to put 0 in there, right? Now, what about our S value? Well, let's look at the last arrow, guys. The last arrow is going up, right? So the spin number is going to be 1/2 positive. And we're doing the Pauli exclusionary principle, which states that no two elements can have the same set of quantum numbers. Well, that's it, guys. You be snarly, and we'll see you back here at Moosing Chemistry.